Okay, in chapter 11, we will be talking about exponential functions and logarithmic functions, things that we can do with both of those and all that. Today, we're specifically looking at exponential functions. Exponential functions have terms with constant bases and variable exponents. So, for example, you have f of x equals 2 to the x power, or f of x equals 3 to the negative x power. The exponential function with a base a is denoted by f of x equals a to the x, where a is greater than 0 and not equal to 1, and x is any real number. So your a value can be a fraction, it can be a decimal, it can be a whole number. It just has to be a real number. The rules of exponential functions are really not any different than the rules that we have had so far this year. If we're multiplying, we can add our exponents. If we're dividing, we subtract our exponents. Power to a power, we're going to multiply those exponents. So a to the x to the y, we're going to multiply that, the exponents x and y. And if we have a negative exponent, we can move that into the denominator. Or if it's already in the denominator and negative, we can move it into the numerator. So we still have the same exponent rules that we had a few chapters back. When we evaluate x values into an exponential function, we're just doing it just like we would any other equation, and we're just going to substitute those values in. So for number 1, x equals negative 2. We're just going to plug negative 2 in for x. So we have 3 to the negative second. We don't like negative exponents, so we're going to move that into the denominator to get 1 over 3 squared. 3 squared is 9, so we end up with 1/9. For number 2, we're doing the same thing. F of 0, we're plugging 0 in for x. 3 to the 0 power. Anything to the 0 power is 1. And then for number 3, when x equals 1, 3 to the first power is just 3. So we're just plugging things in just like we would into any other equation. In 4 and 5, we're going to graph the function and we're going to state the domain and range. I'm going to graph this first before I state the domain and range. Typically, when you are graphing exponentials, it's easiest to make a table. So it really doesn't matter what x values you choose. I tend to choose from negative 2 to positive 2. But again, it doesn't matter. If we plug negative 2 in for x, we did that on number 1, and we ended up with 1/9. If we plug in negative 1 for x, we're going to get 1/3. If we plug in 0, we get 1. If we plug in 1, we get 3. And if we plug in 2, we get 9. So I'm just going to plot those points. So negative 2, 1/9, negative 1, 1/3, 0, 1, 1, 3, and 2, 9. And when we connect those points, we end up with an exponential graph that looks about like that. So remember, when we talk about domain and range, domain are x values, range are y values. So our domain, we don't have any x value that we cannot plug into that equation. So our domain is going to be all real numbers. Your range, if we plug in smaller and smaller x values, we get smaller and smaller y values. But those y values never get below 0. They never actually get to 0. It's just going to become a smaller and smaller fraction. If we plug in bigger x values, our y values are just going to continue to get bigger and bigger and bigger through infinity. So your range is going to be that y is greater than 0. Most of the time, without any sort of transformation to the graph, your range for exponential functions are y greater than 0. There are some exceptions to that, but most of the time, your domain is all real numbers, your range is y greater than 0. Okay, so I would encourage you to try number 5 on your own. You're just graphing it, stating your domain and range. So I'm going to start by making my graph. And then I'm going to use the same x values that I used before, -2 to +2. But it's a 3 to the negative x. So when I plug in -2, 3 to the negative second, 2 negatives make a positive. So it's 3 to the second, which is 9. When I plug in -1, I get 3 to the first, which is 3. 0 is still going to give me 1. When I plug in 1, I have 3 to the negative first, which will give me 1/3. And when I plug in 2, I'll have 3 to the negative second, which will give me 1/9. So when I plot those points, -2, 9, 1, 3, 0, 1, 1, 1/3, 2, 1/9. So it's very similar to the graph in number 4. It's just mirrored. So it's just flipped over the y-axis. So my domain, I can still have any x value that I want, and it will give me a y value. So my domain is all real numbers. My range, my y values are still greater than 0. So they're still not going below 0, but they'll still go infinitely high in the y values. So my range is just y greater than 0. So generally speaking, all of these things are true for graphs that have a form of y equals a to the x power. So a positive exponent with our base of a. So our domain is -infinity to +infinity, which is the same thing as all real numbers. Our range is 0 to infinity, which is the same thing as y greater than 0. We're going to have an intercept at 0, 1, so it's a y-intercept. It increases up to the right, so as we move right across the graph, our graph continues to go up in the y direction. And we have an asymptote at the x-axis. So remember, asymptote means that it does not cross. So it's not going to cross the x-axis. Very similar properties when we have a negative exponent, y equals a to the negative x. Our domain is still -infinity to +infinity, or all real numbers. Our range is still 0 to infinity, or y greater than 0. You still have an intercept at 0, 1. But it's decreasing, meaning it goes down to the right, so it gets closer to that x value as we go to the right on our graph. And we still have an asymptote at the x-axis. So with 6 and 7, we're still doing the same thing. We're still graphing and all of that. Again, it does not matter what x values you choose. You can still choose -2 to +2. You can choose bigger numbers, smaller numbers. It doesn't matter. You just want to make sure you can see that pattern. So in number 6, I'm still going to choose those same 5 values. And when I plug those in, 3 to the negative second is going to give me that 1/9. -1 is going to give me -8/9. 3 to the negative 1 is going to give me 1/3. When I subtract 1, I get negative 2/3. 3 to the 0 is 1 minus 1 is 0. 3 to the first is 3 minus 1 is 2. 3 squared is 9 minus 1 is 8. So when I graph that, you'll notice that it's going below the x-axis this time, and that's because of that minus 1. So that minus 1 is shifting that entire graph down 1 unit. So we've got -2, -8/9, -1, -2/3, 0, 0, 1, 2, and 2, 8. It's still going to have the same shape. It's just that instead of having an asymptote at the x-axis, it has an asymptote at y equals -1. And instead of having a range of y greater than 0, it has a range of y greater than -1. So everything's just shifted down 1 unit. When we look at number 7, f of x equals 2 to the x minus 4. I'm going to change the x values that I pick a little bit, because if I did -2, -2 minus 4 is going to give me -6, and that's quite a small number. So I'm just going to start at +2, and I'm going to go to +6. So 2 minus 4 is -2. 2 to the -2 is 1/4. 3 minus 4 is -1. 2 to the -1 is 1/2. 4 minus 4 is 0. 2 to the 0 power is 0. Sorry, 2 to the 0 power is 1, not 0. 5 minus 4 is 1. 2 to the first is 2. 6 minus 4 is 2. 2 squared is 4. So those are the points that I'm going to graph. So I'm just going to create my graph. So 2, 1/4, 3, 1/2, 4, 1, 5, 2, and 6, 4. So we still have that similar exponential shape where it's rising to the right. It just shifted 4 units to the right from where it normally starts. So instead of having a intercept of 0, 1, we have 4, 1. So everything has just shifted 4 units to the right. So we're going to do the same thing with 8 and 9. The difference is we've got a negative out in front of our base of 2. So we're still going to plot points. And if you want, you can even think of this as -1 times 2 to the x, if that helps. Either way is fine, however you prefer to look at it. But if we plug in -2 for x, we get 1/4 times that negative gives us -1/4. When we plug in -1 for x, we get 1/2 times the negative is -1/2. 2 to the 0 power is going to be 1 times -1 gives me -1. 2 to the first is 2 times the negative. 2 squared is 4 times a negative. So we're going to graph those points. negative 2, negative 1/4, negative 1, 1/2, 0, negative 1, 1, negative 2, 2, negative 4. So when we have that negative in front of our base, it's going to flip that graph over the x-axis. So it's the same shape, just flipped upside down. So if you feel confident, go ahead and try number 9 on your own. It's up to you if you want to try it on your own or if you want to watch one more time, but we're doing the same thing. You can change your x values if you want. I'm going to go ahead and just leave mine the same. So when we plug in negative 2 plus 1 is negative 1. 2 to the negative first is the 1/2 times the negative gives me negative 1/2. When I plug in negative 1, I'm going to get negative 1. When I plug in 0, I'm going to get negative 2. When I plug in 1, I'm going to get negative 4. And when I plug in 2, I'm going to get negative 8. So those are the points that I'm going to plot. So I plot negative 2, negative 1/2, negative 1, negative 1, 0, negative 2, 1, negative 4, and 2, negative 8. So again, my shape is still the same as it is if I had a positive 2 as my base. It's just flipped over the x-axis since it's negative, and that x plus 1 shifts it to the left 1 unit. Okay, so it's just a transformation, but you don't have to do anything for it. You can still plug in points just like normal. Okay, so another exponent that we have is called the natural exponent. So it's when we have a base of e. E is kind of like pi, where it stands for a number that is a never-ending decimal and can't be written as a fraction. So that value e is 2.71828, so on. F of x equals e to the x is called your natural exponential function. So when you graph a natural exponential function, you want to use your calculator to help you find those values for your table. Your E button is the second of the LN button, which is 2 up from the power button, your on button. So I just use the same x values with a natural log function as I would any other function. So I'm just going to use negative 2 to positive 2. So when I plug in my x values, when I plug in negative 2 for x, so e to the negative 2 plus 1, enter, I'm going to get about, I'm just going to do 3 decimals, 368. And then I'm just going to keep repeating it. So when I plug in negative 1 for x, negative 1, e to the negative 1 plus 1 is going to give me 1. When I plug in 0, I get about 2.718. When I plug in 1, I get about 7.389. And when I plug in 2, I get about 20.086. And then we're just plotting those points on our graph. So we're just going to plot those points. Negative 2.368, negative 1, 1, 0 and 2.718, 1 and 7.389. If you want your graph to go all the way up to 20, you can. I didn't want to make my graph that tall, so I'm just going to stop at 7.389. But if you'll notice, it has the exact same shape as all our other exponential graphs. So everything stays the same in that. You're just using your calculator to find what those y values are instead of being able to do any of it in your head. You really have to use your calculator for it. In number 11, cesium-137 is a man-made radioactive element with a half-life of 30 years. A large amount of cesium-137 was introduced into the atmosphere by nuclear weapons in the 50s and 60s. Much of that has now decayed. After T years, 16 grams of cesium-137 decays to a mass of Y in grams, given by Y equals 16 times 1/2 to the T over 30. T is greater than or equal to 0. How much of the initial mass remains after 80 years? So T is your time because it's a half-life problem. So if we want to know how much is left after 80 years, we got to plug that 80 in for T. So in our calculator, we're going to say 1/2 to the 80 divided by 30, which gives you, and you don't necessarily have to write this part down, this step down if you don't want to. Gives us this big long decimal that doesn't end. And we're going to multiply that by 16. So that's going to give us about 2.52. But remember, we're talking about an element and we're talking about a total amount. So you want to make sure you're using your units. So it's in grams. So we've got about 2.52 grams left in the atmosphere. Another common use with exponents is interest. So if you understand interest, you can be a better saver or investor, things like that, as you become an adult, because you understand how you're going to earn more money than what you're putting into something. So after T years, the balance A in an account with a principal P, so that's what you're starting with, is your P value, and an annual interest rate R, always written in decimal form, is given by one of the following formulas. So if it's so many compounds per year, n compounds per year, it's A equals P times 1 plus R over N, all to the N times T power. If it's a continuous compounding, meaning it's constantly earning you interest, it's what we call the PERT formula. So A equals P times E to the RT power. So in our last two examples, we're finding a balance for P dollars invested at your rate R for so many years. We're going to do it though for compounded 1 time a year, 4 times a year, 12 times a year, every day, or continuously. So those are your common compounds for interest. So I'm going to show you what each of those would look like. So remember, if it is compounded specific amounts of times in a year, we're using this formula, P times 1 plus R over N to the N times T power. So for 1 time a year, we have invested $100. We have a rate of 7%, so that's going to be 0.07. We're dividing it by 1 because that's how many times it's being compounded in the year. And we're going to multiply that by the number of compounds times the years. So 1 times 15 is just 15. 0.07 divided by 1 is 0.07. So inside that parentheses, we've got 1.07 to the 15th, which is going to give us about 2.759. And we're going to multiply that by 100. So when it's all said and done, you would be at 275.90 if you never touched it and didn't add anything or take anything out after 15 years. So now we're going to look at 4 times a year. Same exact thing, but we're dividing that 0.07 by 4, and we're multiplying that 15 by 4. So 0.07 divided by 4 plus 1 gives us 1.0175. That 4 times 15, we're going to raise that to the 60th power, which gives us about 2.8318. We're going to times that by 100, and we're going to be at 283.18. So 4 times a year is going to increase our total amount. When we go to 12 times a year, now this is a rounded decimal in the parentheses, so make sure in your calculator you use the actual value and not the rounded value. So when we raise that to 180, we get 2.8489. We times it by 100, and we're at 284.89. When we go to every day, again, we've got rounded values here, so make sure you use the whole decimal answer that's in your calculator. When we raise that to our exponent of 5475, we've got about 2.85736. Multiply it by 100, and we got 285.74. So that's when you're compounding so many times a year. When we compound continuously, remember we're using what's called the PERT formula. So P would be our 100 times e to the rate of 0.07 times our t value of 15. So 0.07 times 15 is 1.05. E to the 1.05 is about 2.85765 times 100 gives us 285.77. So it's not much more than compounded every day, but it still is the most that you can make with interest. So if you can find interest rates that have your values compounding continuously, you end up making the most money. So we're going to do the same thing in 13. I would encourage you to go ahead and try this on your own. You're doing the same thing, you just have new p-values, a new rate, and a new time, but you're still going to do the same n values and then the same continuous value at the end. So I'm going to go ahead and work out number 13. So when I get compound one time a year, I have 4956.46. 4 times a year gives me 5114.30. 12 times a year is going to give me 5152.11. Every day is going to give me 5170.78. And if I have a continuous compound, it's going to give me a total of 5171.42. So that is our first bit into exponential functions. If you have questions, let me know. Get on Google Meet, shoot me an email, but let me know if you get stuck on anything. Don't forget to do your homework because it is due by class time in 2 days from now.